All right, so we're going to look at some problems that reference the central limit theorem here. We've got a population has 4 members, only 4, and their heights are 57, 60, 64, and 65. This is the whole population. Let x bar, that's a sample mean, let x bar be the average from a sample of 2. So each sample is only going to have 2 members in it, okay, of these members. How many possible samples of n equals 2 are there, and what are their means x bar, okay? Well, basically, since we're picking 2, basically what we're doing is we're taking any number and pairing it with another number one time. So, 57 will get paired with 60, 57 will get paired with 64, and 57 will get paired with 65. So we've got 57 and 60. We've got 57 and 64. And then we've got 57 and 65. Okay? All right, so 57 has been paired with all the numbers. Now 60 has to be paired with 64, and 60 has to be paired with 65. So we'll have 60 and 64, and 60 and 65. And note that 60 was already paired with 57, so we're not going to do that again. So now 60 is done. It's been paired with everything. And now the only thing left is 64 and 65. 64 has to be paired with 65. And so now 65 has been paired 3 times. 64 has been paired 3 times. 60 has been paired 3 times. And then 57 has been paired 3 times. So we got them all. So look, there are 6 of them. 1 sample, 2 samples, 3 samples, 4 samples, 5 samples, 6 samples. So how many possible samples of n equals 2? 6 possible samples. Okay? And then here I'm gonna want to use this again up here. So let's get rid of all that. And then it says, what are their means? So we need the mean of 57 and 60. So 57 plus 60 divided by 2 is going to be x bar 58.5. The mean between 57 and 64 is going to be x bar is going to be 60.5. The mean between 57 and 65, that's going to be 61. The mean between 60 and 64, x bar is going to be 62. The mean between 60 and 65, x bar is going to be 62.5. And you can verify these if you want to get a calculator. When you do an average of 2 numbers, you're just going halfway between the 2 numbers. And then x bar, the mean of 64 and 65, is going to be 64.5. Okay, so these are the 6 means of the 6 possible samples of n equals 2. Okay, now we want to know, well, what is the mean of the sampling distribution? Well, this is the sampling distribution. Okay, and the mean of the sampling distribution is the mean of all the means. So we would have to add up these 6 numbers and divide by 6. However, we know that the mean of the sampling distribution is equal to the mean of the population. It's equal to mu, the mean of the population. So really all we have to do is add up the 4 members of the population, 57 plus 60 plus 64 plus 65. I'm going to grab a calculator real quick. All right, here I am at numworks.com. I'm going to hit emulator, and then I'm going to go to full screen, and then I'm going to go to calculator and hit OK. And we're doing 57, 60, 64, and 65. So 57 plus 60 plus 64 plus 65. And we're going to divide that by 4. And that's going to give us 61.5. So that's it. Since the mu is 61.5, then the mean of the sampling distribution is also 61.5. If you were to add up these 6 and divide by 6, you would get 61.5. All right, let's go on to the next question. Okay, so here's question 2. It says, suppose a random variable x is normally distributed and it has a population mean of 23.78 and a standard deviation of 4.52. According to the central limit theorem, for samples of size 17, so n equals 17, what is the mean of the sampling distribution for x bar? Well, we know that the mean of the sampling distribution is the same as the mean of the population. So this is a really easy one, 23.78. What is the standard deviation of the sampling distribution? Now, the standard deviation of the sampling distribution, well, that's called the standard error, right? And we have a formula for that. The standard error is equal to sigma, the standard deviation, divided by the square root of n, and n is 17. So this is going to be the standard deviation, 4.52, divided by the square root of 17. And we'll go ahead to our calculator. So we'll do 4.52 divided by the square root of 17, and that gives us 1.096. Let's make this a 3 here. The 6 will round the 2 up to a 3. So 1.0963. Well, let's just do 1.096. Now I want to warn you here. I'm going to go ahead and write out 6 decimals. 0.96261. 0.96261. 1.0966261. Okay, so here's the thing. If your final answer, if this is your final answer like it is for us, then you can round to 3 decimal places. So our answer is 1.096. That's our answer, okay? But if you're about to plug this number into another formula, then you cannot round to 3. You have to go out to 6 decimal places, okay? And I'm going to show you that in some of the questions that are coming up. All right, so question 3 says a variable x in a population varies, of course, with a mean of 2.3, so mean of 2.3, and a standard deviation, sigma, of 0.53, okay? And it says, suppose a sample is taken from the population. What sample size is needed? So we don't know what n. That's what we're trying to solve for here. What sample size? What sample size is needed so that the standard deviation of the sampling distribution is 0.0765? Well, remember that the standard deviation of the sampling distribution, that's the standard error. And the formula for the standard error is sigma divided by the square root of n. Well, we're told that the standard deviation is 0.53, and we want the standard error to be 0.0765. So we got some algebra to do here. So we're going to replace standard error with 0.0765 equals standard deviation is 0.53 over the square root of n. And we're solving for n here, okay? And so what I'm going to do is I'm going to cancel the denominator. I'm going to multiply by the square root of n on both sides, multiply by the square root of n on both sides, and that'll cancel my denominator. And so now I have 0.0765 times the square root of n is equal to 0.53. And now to get the square root of n, I'm going to divide by 0.0765 on both sides. 0.0765, okay? Over here it's going to cancel, and I'm going to have the square root of n is equal to whatever this is. Well, let's go to a calculator. 0.53 divided by 0.0765. And that gives me 6. Now I need to use as much of this as I can. Don't stop at 3. This is not my final answer, so I need to use at least out to 6 decimal places. 6.928104. And actually, I'm going to make this a 5 because this 5 is telling me to round up the number next to it. So 6.928, 6.928, okay, 105, 105, okay. Now, I don't want this, this is the square root of n. I don't want the square root of n, I want n. So what I need to do is I need to square here, and that means I have to square here. Squaring here will cancel the radical and leave me with just n. Okay, so now I just have n is equal to, I'm going to take this number and square it. So 6.928105 squared gives me 47.998. Now, n is a sample size. Sample sizes are discrete numbers. They're whole numbers. They're not decimals. So what whole number is this close to? Well, 47.99. It's close to 48. And so the answer here is going to be 48. Okay? So the answer is n equals 48. That is the sample size needed so that the standard deviation is 0.0765. All right, let's try another one. Okay, so it says scores on the ACT. That's like the SAT, only it's a different test. It's very similar. It's for college entrance. Scores on the ACT in a recent year were roughly normal with a mean of 20.8. So we're going to say mu 20.8 and a standard deviation of 4.7. So that's sigma equals 4.7. Okay. A sample is taken of 144 students, so n equals 144, and the average of the 144 students, the average of the 144 students' ACT scores is calculated. Suppose you do this many times. Oh, this sounds like the central limit theorem. Suppose you do this many times with the same sample of 144 each time. Then the mean of the average scores will get close to, well, that's the same thing as saying the mean of the sampling distribution. The mean of the sampling distribution of x bar, because x bar is an average of x bar. And that we already learned. The mean of the sampling distribution of the average is equal to the mean of the population. So that's 20.8. We'll get close to 20.8. And the standard deviation of the average scores, well, that's the standard deviation of the sampling distribution, and we call that the standard error. So they're just asking for, well, what's the standard error? With an n of 144. And remember, the standard error is equal to sigma divided by the square root of n. So that'll be 4.7 divided by the square root of 144. And remember, the square root of 144 is 12. So really, we're just doing 4.7 divided by 12. Now, if you want to do 4.7 divided by the square root of 144, that's fine. It'll still give you the right answer. But I know that the square root of 144 is 12, so I'm going to do 4.7 divided by 12. 4.7 divided by 12. That's going to be 0.391666. Now look at this. The probability that the average score is higher than 21. To do that, to do this last blank here, I'm going to need this number. I'm going to need the standard error. So I'm not going to round it to only 3. I'm going to I'm going to go 0.391667. Okay, so it's going to be 0.391667. And now it says the probability that the average score, whatever it is, for 144 randomly chosen students is higher than 21. All right, so this is where we're going to need a z-score. We're going to have to calculate a z-score, and our formula is x bar minus mu over the standard error, which is over sigma divided by the square root of n. Okay? The x bar is what they're asking about. What's the probability that the average score is higher than 21? So they're wanting us to put 21 in for x bar. minus mu, which is 20.8, divided by, now we could just put in 0.391667, but I'm actually going to go ahead and put the whole thing in. I'm going to put in 4.7 divided by the square root of 144. But I want to remind you that the square root of 144 is 12. So I'm going to put this in the denominator and this in the numerator. Okay? And I'm going to do this in the NumWorks calculator. So I'm going to do parenthesis 21 minus 20.8, close, then divided by, and then I'm going to do parenthesis 4.7 over 12, 4.7 divided by 12. Okay, close parenthesis. And that's going to give me a z-score of 0.5106038. We're going to have to put this z-score into the distribution feature on this calculator. So I need to go out 6 decimal places, 0.510638. So my z-score is going to be 0.510638. Okay? And now we're going to put this z-score into the distribution feature. So we're going to go to the home, we're going to go down to distribution, we're going to hit OK. We're going to select normal distribution because we know the central limit theorem says that the sampling distribution of the mean is going to be approximately normally distributed. And then we're going to give it a mean of 0 and a standard deviation of 1 because we want to use z-scores. In order to use z-scores, you have to do a mean of 0 and a standard deviation of 1. And then we're going to hit next. Now, this question is asking higher than 21. So we don't want to use this one. Look, this is the less than shading. It's a left tail. We want to make it a right tail. So we're going to arrow over, hit OK, and we're going to go down to the right tail. And then hit OK. And then we're going to put our z-score right here. And our z-score is 0.510. So 0.510638. 38. And hit execute, and there it is. Look at that. Here's here's the proportion. It says the probability, and a probability is the same thing as a proportion. So the probability is 0.3048. Okay. Now let's put the 023. So the probability, the answer to this question is 0.3048023. 8023. And we could probably get away, oh here, I didn't put the answer up here. This was the standard error, 0.391667. Okay, and then the answer here is going to be 0.304 8023. 8023. Okay, and that's the probability out of 1 that the average score of the average of the 144 students is larger than 21. Okay. All right, let's move on to question 5. All right, this is a 3-part question, A, B, and C. The last one we did was a 3-parter. It was just written weird with those blanks. It says the scores of an intelligence test are normally distributed with a mean of 102.3 and a standard deviation of 15.9. It says, what is the probability that a randomly selected adult from those taking the test scores higher than 130? This is not asking about a sampling distribution. This is asking about a randomly selected adult scores higher than 130. It's actually asking for the probability that one member of the population scores higher than 130. This is not going to be the central limit theorem. This one's actually one we did last week where it's just z equals x. X is one observation, and that's one adult scoring higher than 130. So x minus mu over the standard deviation. No standard error here. This is not a sampling distribution of the mean. So z is going to be equal to 130 minus the mean, which is 102.3, divided by the standard deviation, which is 15.9. So first we need a z-score, and then we need to put it into the normal distribution on the NumWorks calculator. So we're not going to use this yet. We're gonna go home. We're going to go to the calculator, and we're going to calculate 130 minus 102.3. 130 minus 102.3. Then we're going to divide that by the standard deviation, which is 15.9. It's not asking about a distribution of the means of a bunch of samples. It's just asking about one adult, and that's why we're doing it the other formula from what we did last week. So this is going to give us a z-score of 1.742138. 1.742138. 1.742138. Now we're going to turn that into a p-value from using the normal distribution. So we're going to go home here. We're going to go down to distributions and hit OK. And look, we're still in the normal distribution. Normal distribution. And it's asking for higher than 130. And so we want to use the right tail, which is exactly what we have here. If it asked for less than, we would have picked this one. If it asked for in between, we would have picked this one. But since this one is asking for higher than, we're going to pick this one with the right side shaded. Okay. All right. And now we're going to put in the z-score, which is 1.742. 1.742. 138. 138. Enter. And look, here it is. Here's our 0.04. Look, it's not very much. You can see it down here. It didn't shade very much. 0.0407. I guess we can stop. Well, we'll put a bunch of it in. 0.0407. And then 0407, 4215. 4215. You know, you can probably only go to either 4 or 6 decimals, but I'm just trying to make sure we cover all the bases by showing you the whole number. Okay. All right. Part B now says if a sample, okay, Part B, if a sample of 37 adults is given the intelligence test, so now we have a sample size of 37. What is the mean and standard deviation of the sampling distribution? Now it's asking about the sampling distribution, okay? And we know that the mean of the sampling distribution is always equal to the mean of the population. So the mean, and one way we can say this is we can say the mean of all of the X bars. This is how we write the mean of the sampling distribution. It's going to be the same as the mean of the population, which is 102.3. But the standard deviation of the sampling distribution, that's the standard error, which is sigma divided by the square root of n. And sigma here is 15.9. And the square root of n, well, n is 37. See? 37. We'll key that into the NumWorks calculator. So we got to go home and we got to go to the calculator here, up here. And we'll do 15.9 divided by the square root of 37, and that gives us 2.613944. We'll make this 3 a 4 because of this 8. Okay, so 2.613 944, and that is our standard error. That's the standard deviation of the sampling distribution for X bar. All right, part C. What z-score corresponds to a mean score of 95 for those 37 adults? Okay, well, this is now asking for us to identify the z-score for a sampling distribution mean. So now it's X bar minus mu over sigma divided by the square root of n. Okay, because it's asking about the sample. It's not asking about a single adult. Up here, it was a single selected adult. Now it's the mean of 37 adults. That's why we're using this formula. So z is going to be equal to, they're asking what z-score goes with a mean of 95. So we're going to put 95 in for x bar. 95 minus mu is all the way at the top, 102.3, 102.3, divided by sigma, 15.9, 15.9 divided by the square root of 37. Okay. All right, so we're going to do parenthesis 95 minus, what is it, 102.3, 102.3, close parenthesis, divided by, and now parenthesis, standard deviation, which is 15.9, 15.9, divided by the square root of 37, square root of 37. And execute, and we get negative 2.79271. This 4, I'm going to make that 4 a 5. So negative 2.7927, 792715. All right, that's the z-score. That's what they asked for. Now it says, what is the probability that the mean score x bar of these adults is below 95? Well, all they're asking for is the proportion below the z-score of negative 2.792715. All right, so it says what is the probability? So P equals, so we're going to go back to the numworks. We're going to go home. We're going to go down to the distribution. Okay, we're still in the normal distribution, but this question is saying below 95. Below 95 means that we want to switch this to a below. We need a left tail test. That's going to be the left shading. All right, and now we got to put our z-score in here, and our probability will be in this box. So we'll put our z-score here, and that's negative 2.79, negative 2.79. 2715, 2715, execute, and here's our answer. The probability is 0.0026. We'll stop at 0.002. Well, let's go to 13. 0.002613. 0.002613. And that's it. That's the end of question 5. All right, here's our last question, question 6, and it's also in 3 parts, just like question 5 was. It says a random variable x is normally distributed. That means that we can automatically use the central limit theorem because the variable itself is normally distributed, even though it's a small sample of 13. With a mean of 35.27 and a standard deviation of 4.19. Suppose a random sample of n equals 13 is taken. What is the probability that the mean of the sample, yup, that's definitely our z equals x bar minus mu over sigma divided by the square root of n. It's asking, look, it's asking about the mean of the sample. What's the probability that the mean of the sample of 13 is going to be less than 33.5. So we need a z-score that goes along with 33.5. So we're going to put 33.5 in for x bar. So z equals 33.5 minus the mean of the population, which is 35.27, 35.27, divided by sigma 4.19 over the square root of n, which is 13. All right, so we'll key this into the numworks calculator. Let's go back to the calculator. Okay, we're going to do 33.5 minus 35.27. So 33.5 minus 35.27, close parenthesis, divided by parenthesis. Our sigma is 4.19. That's our standard deviation, 4.19, divided by the square root of 13. And that gives us negative 1.52310. And this 8, this 7, is going to tell this 8 to become a 9. Negative 1.523109. Negative 1.52310. That's our z-score. And now we just, because it says a probability, Now it says less than, so we got to turn this z-score into a p-value. All right, so to do that, we are going to move over to the NumWorks calculator, and now we got to switch to the distribution feature, so we got to go down to distributions, hit OK. This says less than. Is our question saying less than? Less than, it sure is, so we're going to use this one where the shading is in the left side. That's the less than shading. We're going to put in a z-score of negative 1.523, and it's already highlighted here, so negative 1.523, 109, 109. Execute, and look at this. Here's our probability, 0.0638657. 0.0638657. 657. That's our answer. All right, so now do part B. What is the probability that the mean of the sample? That's the same question. Mean of the sample will be greater than 38. So it's the same kind of question. We're going to use the same formula, but instead of putting in 33.5, we're going to put in 38. All right, so z equals 38 minus 35.27 divided by same standard deviation, 4.19, over the square root, same sample size, 13. So the only thing we're changing is the 38. That's it. Okay, so when we go to the calculator, let's go to the home button, then up to the calculator, hit OK. I can use the same calculation I used last time. I'll just grab this and I'll change the 33.5 into a 38. And now it's still the same. Look, minus 35.27, 4.19 divided by the square root of 13. So when I hit execute, I get 2.34920. This is a 1, but the 6 is telling this 1 to be a 2. So 2.349202. 2.349202. 2.349202. Now we're going to turn that into a p-value using the NumWorks calculator. Go to the home, go down to distributions, hit OK, normal distribution. But look, this says greater than 38, greater than. So we don't want this. We don't want the less than shading. We want the greater than shading. So we're going to come over here, hit OK. We're going to go down to the greater than shading and hit OK. Now our z-score is 2.349, 2.349, 202, 202. And then hit execute, and our probability, look at how little, it's above that number, so it's only a little bit of shading down here, 0.0094. So the answer is 0.0094, 0684, 0684, okay? All right, only one part left, part C, and it's a between. Look, between 33 and 37. And that means when we go here, we're going to have to change from this shading to the between shading. So we're going to have to go up and choose this one where we can put in 2 z-scores, okay? And in order to put in 2 z-scores, we're going to have to calculate 2 z-scores, one for 33 and one for 37. All right, so z is going to be equal to 33 minus the mean of the population, which is 35.27, divided by the same thing, 4.19 over the square root of 13. Okay, and so let's go back to our calculator. We'll go home, up to the calculator, okay. We'll grab this again, it's the same calculation. We're just going to change the 38 to a 33. Whoops, 38 to a 33. And so the z-score here is negative 1.953365. All right, so negative 1.953365. 3365. Okay, so that's one of our z-scores. That goes with 33. Now we need a z-score for 37. So we're going to do z is equal to 37 minus 35.27 divided by 4.19 over the square root of 13. Okay, go to the calculator again, and now look, we can again grab the same calculation. Whoops, I hit a button. Hang on, there we go, okay. But we're going to change the 33 now to a 37. 37, execute, we get 1.488688. 488,688. 1.488688. So now we're going to go into the calculator and we're going to put in this z-score for the smaller z-score and this z-score for the larger z-score. So we'll go home, then down to distributions, hit OK. And look, we're going to put the smaller z-score here and the larger z-score here, okay? And x is in between them. Smaller z-score is negative 1.95, 3365, 3365. All right, and then the larger z-score is 1.488688, 1.488688, and then execute, and here is our answer. There's our, look, that's a lot of shading, and so it's 0.906, that's a lot. So the final answer here is P equals 0.906, 0.906, 327, okay? And that's it, whoops, and that's it. That's how we use the central limit theorem to calculate the probabilities that a sample will have a certain mean that's either larger than a number, smaller than a number, or between two numbers.